Hello everyone. Today we will proceed for refraction from the spherical surfaces. Earlier we have discussed the refraction from the plane refracting surfaces, transparent surfaces or mediums. Now we will discuss the refraction which is happening through a spherical transparent medium. So in basic there are two kinds of spherical refracting surfaces, just as you can see. One, it is which is bulging outside the curved surface or spherical surface. If it is bulging outside, then it is called as convex spherical refracting surface. And on the other hand, if this spherical surface it is bent inward, then it is called as concave spherical refracting surface. All other things are very similar, as you already know. This is the principal axis, the pole, the center of curvature, the radius of curvature. Apart from this, the sign conventions which also remains same, that all the distances are to be measured from the pole of the refracting surface, right? All the distances are to be measured from the pole of this refracting surface, either convex spherical refracting surface or concave spherical refracting surface. And opposite to the incident ray, all the along the direction of incident ray, all the distances from the pole of the refracting surfaces to be measured are taken as positive, and opposite to the incident ray, all the distances are which is measured from the pole of the spherical refracting surface are taken as negative. Similarly, above the principal axis, all the lengths are taken as positive, and if we are measuring the lengths below the principal axis, then we take them as negative. So in order to use and discussion the theory of these spherical refracting surfaces, we assume that object is of point size and the object is always lying on the principal axis. तो यहाँ पे हम ये मान के चलेंगे कि ऑब्जेक्ट हमेशा एक पॉइंट साइज का है और वो प्रिंसिपल एक्सिस के ऊपर लाई कर रहा है. साथ में और क्या अज्यूम करते हैं, द इंसिडेंट एंड रिफ्रैक्टेड रेज मेक स्मॉल एंगल्स विद द प्रिंसिपल एक्सिस. जो इंसिडेंट रेज एंड रिफ्रैक्टेड लाइट रेज हैं वो प्रिंसिपल एक्सिस के साथ बहुत ही स्मॉल एंगल बनाती हैं. एंड ऑल्सो द थर्ड assumption which we make here in order to discuss further is that aperture of this spherical refracting surface, it is taken as very small. This is the aperture. We take the aperture to be very small because only in that case the angles will remain quite small. So in order to discuss further, we make use of these three assumptions. Now let us proceed in order to derive and understand a very important formula related to this spherical refracting surface. Spherical refracting surface के बारे में ये जो फॉर्मूला है ये बहुत ही इंपॉर्टेंट होगा in order to understand the formula which is driven for the lens, which is a convex and concave on both sides, which is the combination of both convex spherical refracting surface and concave spherical refracting surface. So let us proceed. So ये डेरिवेशन याद रखना और इसको सॉल्व करना आपके लिए इजी होगा अगर आप एक चीज़ का यहाँ पे टेक्निकली या ट्रिकी तरीके से ख्याल रखेंगे. वो क्या है कि ये जो नोटेशंस हैं, ईच एंड एवरी नोटेशन इन दिस डायग्राम, ये सभी तरह के केसेस के लिए हो सकता है. ऑब्जेक्ट रेयर मीडियम में है एज इट इज़ विजिबल हेयर, हो सकता है ऑब्जेक्ट जो है वो डेंसर मीडियम में हो, इमेज रियल भी हो सकती है, वर्चुअल भी हो सकती है. It may be a convex surface or it may be a concave refracting surface. तो in all cases अगर ये जो notations हैं ये सेम रखेंगे तो ये जो derivation है इसको याद रखना आप लोगों के लिए बहुत ही easy होगा और समझना भी easy होगा. जैसे ऑब्जेक्ट को O से लिख रहे हैं, इमेज को I से लिख रहे हैं, इस पॉइंट को A से और इस पॉइंट को M से लिख रहे हैं. पोल तो ऑब्वियसली P से ही लिखा जाएगा, सेंटर कर्वेचर को C से ही लिखा जाएगा. और ये जो एंगल्स हैं, ये इंसिडेंट रे जो एंगल बना रही है विद द प्रिंसिपल एक्सिस, रिफ्रैक्टेड रे एंगल बना रही है विद द प्रिंसिपल एक्सिस, और ये नॉर्मल एट द पॉइंट ऑफ इंसिडेंस, जहाँ पे लाइट रे इंसिडेंट हुई फ्रॉम द ऑब्जेक्ट, उस पॉइंट के ऊपर ये जो नॉर्मल है विच पासिस थ्रू द सेंटर ऑफ कर्वेचर, वो जितना एंगल बनाएगी. अगर ये नोटेशंस आइडेंटिकली यूज़ करते रहेंगे तो ये जो डेरिवेशन है हमारे इस आर्टिकल की, फॉर दिस फॉर्मूला इट विल बी वेरी इजी टू अंडरस्टैंड एंड रिमेंबर. तो यहाँ पे ऑब्जेक्ट इट इज प्लेस्ड on the principal axis. Object is of point size, so light ray coming from it is called as incident ray. It is incident on this spherical refracting surface. For the very first case we are taking that the spherical refracting surface is convex. It is the convex spherical refracting surface. On the convex refracting surface, this light ray undergoes refraction and it bends. Convex spherical refracting surface, it will always try to bend the light rays coming from an object at the denser medium. It will try to bend these rays towards the principal axis, which is passing through the, or we can say towards the normal and towards the principal axis, which meets the principal axis at some point I. So this is incident ray, this is the refracted ray. At this point of incidence A, we are drawing a normal Cn, which passes through the center of curvature of this convex spherical surface. The angle made by the incident ray with the principal axis, let us call it alpha. Angle made by this refracted ray with the principal axis, we are calling it beta. And the angle made by this normal at the point of incidence, it is making an angle gamma with the principal axis. We are calling it gamma. We are drawing a perpendicular from this point A on the principal axis, which meets at point M. So this is AM is the perpendicular. All other notations you already know. Now we proceed. So now we can proceed in order to derive the formula. So for this, in the very first case, we will take this triangle OAC. So in this triangle of OAC, we will make use of exterior angle property, which simply says that the exterior angle of a triangle, it is always equal to the sum of two opposite interior angles. So I is the exterior angle here in this triangle OAC. So I, which will be equal to sum of two opposite interior angles. So these alpha and gamma are the opposite interior angles for the exterior angle I. So I will be equal to alpha plus gamma. So this you can write here from the triangle AOAC by using exterior angle property. Angle I, it is equal to angle alpha plus angle gamma. Similarly, in triangle ACI, gamma will be the exterior angle, and therefore this will be, according to exterior angle property, this will be equal to R, which is the angle of refraction which this refracted light ray makes with the principal axis, plus beta, R plus beta. So gamma is equal to R plus beta. You can write this here, that from triangle ACI, by using exterior angle property, angle gamma, which is the exterior angle here for this triangle, which will be equal to R plus beta, the sum of two opposite interior angles. So from the very first equation we calculate I, and from the second equation we calculate R. So for R we take beta to the other side, so R becomes equal to gamma minus beta. So these are the two equations here. Now we've tried to find out the values of alpha, beta and gamma, because we have already assumed that the angles made by the incident ray, refracted ray and this normal with the principal axis are very small, because the aperture of this spherical refracting surface is very small. So that means these angles alpha, beta or gamma, they can be replaced by their tangents. So alpha is very nearly equal to tan alpha, beta is very nearly equal to tan beta, and gamma, it will be very nearly equal to tan gamma. And we can write the values of alpha means tan alpha from the triangle OAM. So we will write the values of alpha, beta and gamma from triangles OAM, from triangle AMI and from triangle AMC. AM will be common to all the three triangles, and we will find from these three triangles the value of tan alpha, tan beta and tan gamma, which are nothing but the values of alpha, beta and gamma here, right? Once again, because aperture of this spherical refracting surface is taken as very small, so these angles alpha, beta and gamma will be very small. Because of this, these angles can be replaced by their tangents. Just like alpha, it will be approximately equal to tan alpha. Now it is tan alpha. So from this triangle OAM, we are writing the value of tan alpha, which is perpendicular AM upon base OM or MO, just like this. And similarly for tan beta, AMI in this triangle, tan beta, it will be equal to AM upon MI, just as here. Because angles are small, alpha, beta, gamma angles are small, so therefore tan alpha is nearly equal to alpha, tan beta it is nearly equal to beta, and tan gamma it is nearly equal to gamma, right? So this is the second step we are doing here. In the third step, we are applying the Snell's law here. According to Snell's law, the relative refractive index of medium 2 with respect to 1, it will always be equal to sine of angle of incidence to the sine of angle of refraction. So it is sine I upon sine R. This is the angle of incidence here. This is the angle of refraction, which will be equal to mu 2 upon mu 1, where mu 2 is the refractive index of this medium of this refracting surface, and mu 1 is the refractive index of this medium, which is air here, for example. So it is mu 2 upon mu 1. From here, because angles remain quite small, so they will be very nearly equal to their angles. So sine I is very nearly equal to I, and sine R it will be very nearly equal to R. So that's why we are in place of sine I upon sine R, we are using simply I upon R, because angles remain quite small. So this will be equal to mu 2 upon mu 1, and on arranging it we get this equation. Now the thing is that we have to substitute the value of I and R from here. But before substituting here, what we do, we substitute the value of alpha, beta and gamma from these three ratios to here in these two equations. I is equal to alpha plus gamma and R is equal to gamma minus beta. We are substituting the values of alpha, beta and gamma, and then whatever equations we get for I and R, we substitute them here, I and then here as R, right? So that will make our task easy. Now after rearranging these and making some simplification, we will get this equation. Here we are replacing M in the denominator, we are replacing M with the P. Why we are relating it or replacing it with P? Because for the small aperture, this M will lie very close to P. So therefore, if we are measuring the distance from M, that means it will be very nearly equal to the distance being measured from P, the pole of the mirror. Now we can make use of sign conventions here, because we have sign conventions for the distances being measured from the pole of this spherical refracting surface. So what we just have did, we just have written the two equations for angle of incidence and angle of refraction by making use of triangles OAC and then ACI, by making use of exterior angle properties. Then we have just found alpha, beta and gamma from these right angle triangles OAM, AMI and AMC, and then we substituted for alpha, beta and gamma from here in these two equations. And when we get I and R, we substitute these values of I and R here in the Snell's law, and we arrange this equation just like this, and we make use of approximation that for the small aperture of this spherical refracting surface, M lies very close to the pole of the spherical refracting surface, so we just replace M with the P. So and this MA, it will just cancel out on the both sides. Now we get this equation. So this is the only important thing here to remember. Now by making use of sign convention, PO means PO, the object distance, PI, the distance of image, and PC, the distance of center of curvature. All the distances are to be measured along by making use of the sign conventions. So by making use of sign convention, PO, it is the distance being measured opposite to the direction of incident ray. It will be taken as negative, so we make use of minus sign here. So we are writing PO as minus U. Similarly, PI, it will be taken as positive because it is being measured PI along the direction of incident ray, positive V, and PC, again it will be positive R because it is also being measured along the direction of incident ray. Let us substitute the values of these three values here, quantities here, and we see that we get this equation. Whatever we get here, this is the very important equation for a spherical refracting surface. You can also try the same equation for deriving the expression for the same equation, same situation whenever object is in the rarer medium and in the rarer medium, just like this, and but the image is formed is we can say virtual image is formed, right? Or in this case it is the real image because object is in one medium and image is formed in the other medium. Or you can also take the other case, if object is placed in the denser medium and image is formed is either in rarer medium or in the same medium. Or you can also take that if this spherical refracting surface is of concave type. In all the cases you will get some formula. This is the case for the convex surface whenever object is formed in placed in rarer medium and image is formed in the denser medium, right? Or in other way we can say that it will be only formed in the denser medium only virtually. That means the image will be formed in the same, we can say, medium. So it will be the virtual image. Keep this thing in mind that you have to keep all the notations same in order to make your derivation easy to remember in any case. So you get a formula here, you get a formula here. Similarly, you will get a formula here just like for all the different cases. This is for the concave surface. In all cases, you will get only two kinds of the formula, right? In all cases, total you will get only two kinds of formulas. One which will be just like this as we have just found it here, and other one which will be different from this one slightly. So in what sense it is different? You can compare these two. It is mu2 here in this equation, and in place of mu2 we have mu1 here, and on the other side of this equation we have mu2 minus mu1 here, and here mu1 minus mu2. So only these two equations are obtained at the last. So only thing you have to remember is that you keep the notations in each and every article or situation same, whether it is a convex spherical surface or concave spherical refracting surface, whether image is formed in real or virtual. So in all cases you will get only these two equations. If you want to see, you can just compare these two equations. So these equations are nothing but the equation which we have received earlier. Only the difference is for this equation, right? So it is mu2 and mu1 here and mu1 minus mu2 here. Earlier it was mu2 minus mu1 here, and so this is the only difference. So in all we will get only two equations. So in order to understand the concept of lenses further, we have to remember only these two equations. So I want you to practice these two equations so that on the next day we can understand the formula which will be derived for a lens, which will be identically curved on the both sides, right? So it will this will also be a spherical refracting surface which is spherical on both the sides. So we will get the same two equations as we have discussed here. right? So by using these two equations, we will derive a very important formula called as the lens maker's formula, and from this formula we will derive the lens formula, or we can say lens equation further. So these are the only crucial steps to be followed here. You have to understand this derivation first, and then you will understand that there will be two equations just like this. In these two equations you will remember this formula, and then we can derive the expression on the next time when we will discuss it, the formula for the lens called as the lens maker's formula. That's all. Thank you.